No, we're a bit stunned. So sorry. First of all, good morning to everybody. Frank Hasenbauer, I'm the session chair for this one. I should have my presenters under control. Apologies for not being able to have them under control.
What I would suggest, Frank, is that exceptionally
we go into the...
You rearrange because you've got this is a panel session.
This is a panel session, so we could do that. So Tony, so the other two presenters, Tony Nerone from NASA and Takashi Yamane from JAXA are here. So I would suggest we start with Tony, then go to Takashi, and then if Gaudy sort of finds this place in the next sort of 40, 50 minutes, she gets a chance to give in her presentation then. So can I ask the guys from the Technic, please, to then go to the second presentation of this panel? That looks good. So can I introduce Tony first of all? So Tony Nerone is the program manager for the Hybrid Thermally Efficient Core, HYTEC program at NASA, which is part of the Sustainable Flight Partnership in the US, which you all will have heard about. And Tony has 25 years at NASA, so he has spent some time in this, and of course he will talk to us about how to drive compressor, combustor, turbine efficiency upwards, drive new materials, and electrification into the core. So the floor is yours now, Tony.
All right. Good morning. Sorry for the schedule change. So I'm Tony Nerone. I'm the project manager for HYTEC, the Hybrid Thermally Efficient Core project, which is part of the Sustainable Flight National Partnership in the U.S. that you've heard about this week in a number of different presentations. This is the format for SFMP, all the different areas that are being worked. HYTEC is focused on the engine efficiency part on the lower right, focused on the 5 to 10% fuel burn from the engine core, which will be part of the overall 25 to 30% fuel burn reduction that we're going for on the next single-aisle aircraft. But HYTEC is focused there, but also some of the electric aircraft propulsion. There's a hybrid electric element, which is why we call it the Hybrid Thermally Efficient Core, and I'll talk about that in a little bit. If this chart's been shown this week too, but just to reorient and refresh everyone's memory, these are all the projects that are part of SFMP. You have the X66, SFD, some transonic truss-braced wing work in AATT, the composites work in HYCAM, EPFD for electrification, and then HYTEC is right there, where we're going to be doing a core demonstration to TRL6 to demonstrate that hybrid thermally efficient core. We have selected our partner for that. I'll talk about that a little bit later. And the intention is to do that core test in 2028 and then wrap the project up in 2029. So what is HYTEC? What are we doing? Why are we doing it? Our goal is to accelerate next generation turbine engine technologies for small core engines in the single aisle class. So we're focused on sufficiency, durability, performance, that hybridization element, and sustainability for that entry into service in the 2030s. Breaking that down a little bit more, our specific project objectives are to get that 5 to 10% fuel burn versus the 2020 best-in-class engines, and that's just from the core. We're not talking about fuel burn benefits from the fan or other things, just from the engine core, 5 to 10%. Up to 20% power extraction and insertion for the hybridization element. We're trying to pull electric power off the engine and put electric power back on both spools of the engine, and also demonstrate up to 80% compatibility with up to 80% SAF, but ideally we're shooting for 100% SAF in the combustion. So when we're done, we expect to have this 5 to 10% fuel burn benefit and hybridization and have these fully compatible with sustainable aviation fuel. So the HYTEC metrics, we're focused on single aisle for small core. What does that mean? We were targeting engine thrust class of 25,000 to 35,000 pounds, about 110 to 150 kilonewtons, which puts it squarely in that A320, 737 class. That's what we were focused on. So we weren't looking at smaller engines. We're only looking at single aisle and not larger engines for twin aisle. So small core means that. And so the significance of that when we look at our metrics, and I'll go into some more detail, but our key performance metrics that are related to the small core are engine bypass ratio. We want to shoot for greater than 15 in this thrust class, an overall pressure ratio of greater than 50, and the high pressure compressor exit corrected flow of less than 3 pounds per second, right around 1.4 kilograms per second. So pretty small core. The way I like to hear this, there's a good way that this gets described. It's essentially, if this is successful, a business jet size core powering a single aisle fan. So it's pretty significant. And this, I think, really illustrates the significance of what we're trying to do and how big of a jump we're trying to make in engine efficiency and technology. We pulled this figure from a paper that was written in 2015, AAA paper. And at that time, NASA in 2008 came up with the M+3 goals, which was basically 3 generations forward in aircraft from 2008. So that was looking at the 2030s back in 2008. And that blue or that green dot on the left and that green line kind of illustrate what those M+3 goals were, where we wanted to go in the 2030s, stated back in 2008. At the time this paper was written, all the engines in service were the green and blue dots in the shaded areas. So those were engines that were in service in 2015. And you can kind of see overall pressure ratios, in the 5 pound per second core size, we're only in the 30s. By the time you got to OPERs in the 40s, you were at really large cores, 6, 7, 8 pounds per second, pretty large. And that was that's where everything was in 2015. And the gentleman who wrote this paper pointed out that there were architectural limits and material limits to really pushing it any further than that. Temperature limits for materials. Could you have an axial compressor? Would you have to change the compressor architecture to go any further? And so this was back, 9 years ago, and that was the state of where things were. So our baseline is a 2020 baseline. So I added those 2 green dots there in the red circle, say the HYTEC baseline. We all know what those are. One of those is the LEAP, and one of those is the GTF from the US. And those were the engines that came out in 2020. And you could see they were an incremental improvement over the ones that were in service in 2015 in the shaded areas. They were higher OPER, but the core sizes were still around that 4.5 pound per second size core. And so where we want to go is the large red dot, the HYTEC objective. And you can see that's not just an evolutionary incremental improvement. It is a large jump where we're going significantly down in core size below 3 and up above 50 OPER. So this is actually approaching those M+3 goals roughly 25 years later when we get there in about 5 years. And to me, that's really a good story that NASA came out with these really aggressive goals in 2008. And by 2029, we will be very close to actually achieving those goals if we're successful. So our other key performance parameters that define HYTEC here, some of these you've seen already, but there's the 5 to 10% fuel burn benefit that we want to hit. There's a full success and a minimum success requirement. We want that engine bypass ratio of greater than 15, the OPER of greater than 50. But we also want to increase engine durability. So even though we're going to smaller cores and higher temperatures, we want to increase the durability by 5%, not decrease or maintain it. There's the electrification part where we want at least 20% power extraction and insertion at altitude conditions. The small core, smaller than 3 pounds per second. Compatibility with 100% SAF. And that last one is hybridization of only 5 to 10%. When we do our core demo, it's not going to have a low pressure turbine, it'll just have a high pressure turbine. So if you're doing single spool, we cut the numbers in half for only 1 spool. So the way we approached the project to accomplish these goals was to divide the project into 2 phases. The first phase, we were doing individual technology development efforts, rig tests, things like that, focused on certain technologies. And the goal was to achieve a minimum of a TRL 4 in the first phase. Some technologies might hit TRL 5, and basically get them ready to a point where we could integrate them into a core demonstration and do an integrated test at the end to show that we met all those project objectives. So right now we're into phase 1. And we have just awarded phase 2, where now we're taking successful or technologies that have achieved TRL4 at least, and we're going to integrate them into that core demonstration where we demonstrate TRL6. This is the technology portfolio from phase 1, and we intentionally focused on areas where NASA could have an impact. There's other technologies we could have put into the portfolio, but we wanted to look for things that we could really help accelerate. And so it's turbofan power extraction, which is that hybrid electric piece, combustion technology, so it's small core combustor, also with that full compatibility with sustainable aviation fuel, and also advanced materials in the combustor section, ceramic matrix composites with environmental barrier coatings, so we can increase the temperature and durability in the combustor, and also CMCs and EBCs in the turbine section, again, for increased durability and higher temperature capability. And then aerodynamics. As things are getting smaller, turbines getting smaller, compressors getting smaller, all those aerodynamic challenges are there to get that performance, particularly if you want to get a 50 OPR. And your blades are getting smaller, but the clearances are staying the same. So there's a lot of aerodynamic tricks that we have to put into these engines in order to achieve the same power level. This smaller core still has to generate the same level of power to turn that big fan. And making it smaller and getting the same amount of power out of it is no easy task. So that's why we're focused on some of these advanced cooling and aerodynamic designs in the turbine section and using casing treatments and things like that in the compressor section to achieve that. These are the contracts that we awarded in phase 1. So it's to GE Aerospace and Pratt Whitney. We have a compressor contract, a couple different ones in materials, a couple in turbine, a sustainable aviation fuel combustion contract, and then one for power extraction, hybrid electric. Right now we had our 8 contracts originally in total. 3 of them are already completed. 3 of these are done, and they've been successful. And the rest of them should complete in about the next year. So we're actually wrapping up phase 1. Phase 1 is winding down, and so far we're on track that I think only one of these contracts will not achieve its technical objectives. So except for one, they all are on track. They either have or are on track to meet their technical objectives. So we've had really good success in phase 1. For instance, we've achieved TRL5 just a couple months ago with environmental barrier coatings. The small core turbine concept reached TRL4 from GE, and then we've also got the liner, the CMC EBC liner, to TRL5. And one thing I want to mention is that when we did this, we didn't just intend to have contracts and just say, well, we're doing all cost share contracts. All these are at least 50-50 cost share between NASA and the companies. But it's more than that. We're putting in more than 50% at NASA because we also utilized a lot of our subject matter experts in our facilities in phase 1. This wasn't just a matter of giving money to industry to say, go develop these contracts and we'll offset your cost. A lot of the testing for a lot of these contracts was completed at Glenn Research Center in Cleveland, Ohio, and we did a lot of the testing that contributed to some of these contract success. We've done turbine testing, we've done compressor testing, turbine aerodynamics anyway, and a lot of materials testing. And this slide is just an example of one thing. This is some materials testing we did at Glenn. On the left there, you can see that's a burner rig with a 3,000 degree burner. And we upgraded that facility so it could run 24 hours a day, 7 days a week, and put lots of hours on CMC, EBC coupons. And that's how you achieve TRL4. You basically get it real hot and keep it hot for many, many hours and see how the coating holds up. And then what we did, once that coating, the coatings that were successful with that, we moved them into a combustion rig. And on the right there, that's the combustion test section that we built in the machine. And we did that testing this spring where we can simulate the combustion environment in a facility. So it's not just the temperatures, it's the temperatures, the pressures, and combustion air that you would see similar to an engine. And so those coatings that survived TRL4, we put into the combustion rig, and then they survived there, so now they've achieved TRL5. So all that was done at Glenn, and like I said, we've done even hybrid electric work, a lot of in-house work to support these contracts. So when we get to the end of phase 1, we wanted to do an assessment of how well we did. Obviously, when we're done and we've done a core demo, we can go through all those metrics I showed earlier, the fuel burn, and how is this going to translate to OPER, how is this going to translate to bypass ratio. But we didn't want to wait until 2029 to figure out, are we on track, what are we doing? So we developed a methodology to say, let's do an assessment at the midpoint when we're done with phase 1 to see how we're doing with our technology development. And so we built models using publicly available information for both a LEAP and a Pratt GTF. These are the numbers that we got for what those engines look like today. The LEAP 1B has a bypass ratio of 8.6, core 4.23 pounds per second. The Pratt one is a little bit bigger bypass ratio at 12, and about the same size core, a little under 4.5. And so this is basically our 2020 baseline that we're going to compare to throughout the project. So what we did was said, okay, we don't have the vision system yet. We don't know what the new engine's going to look like in 5 years to do the assessment. So our team built these models and said, well, what if we took some of the technologies in phase 1 that are TRL4 and we retrofitted them into a current engine? We put them into a LEAP, we put them into a GTF. What would that look like and what would be the effect? And so here are the answers to those questions. This is assuming, however, that all the technologies were fully successful. So this is a projection, I will say that. When we're done, we will go back and rerun these models with our actual data and results from the contracts, and then come back and see what our final results were. But that said, these are all the technologies that we infused into a LEAP, and when you look at it, it's pretty dramatic. Even just taking our technologies and retrofitting them into a current engine, which admittedly is not the easiest thing to do, but it could be done, you already get a 5.2% fuel burn benefit. That's huge already. The bypass ratio jumps from 8.6 to 10.8, which is not insignificant, and the core size drops all the way down to 3.25. So that's significant improvement even on a current product. And we did the same projection with a Pratt GTF. Same thing, infusing some of those technologies. The fuel burn benefit was even bigger. It was over 6%. The bypass ratio jumped up to our full success criteria over 15, and the core size also dropped dramatically to 3.33. So if we're successful, this is a good check halfway through the project to show we are making progress, we're moving toward those goals. Some of these aren't quite full success yet. We want to get to 12 or 15 bypass ratio, not 10. We want the core under 3. These are still over 3, but we're getting close, and it shows that we're on the right track. So when we get to the end and have an actual brand new core vision engine, we're hoping that this is indicating that we will meet all those full success criteria. So I mentioned that phase 1 is winding down. We didn't wait till phase 1 ended. We've actually awarded phase 2 already. To keep on track schedule-wise, we had to do that. So we selected GE Aerospace for our phase 2 contract. That was just done earlier this year. It's, again, a minimum 50 contract cost share. We're putting in $68 million, and it's a 5-year period of performance. So this is where we're going to integrate all the technologies into a core demonstration and complete that by the end of 2028 to demonstrate TRL 6. And so this is the technology portfolio for phase 2, which looks strikingly similar to phase 1, which is good because we're carrying forward a lot of the technology from phase 1 into phase 2. We have hybrid electric, so we're going to do power extraction and insertion on the core demonstration at simulated altitude conditions. We have high pressure compressor carrying forward, the combustion, the small core combustor, compatible with SAF, the enhanced combustor materials, again, bringing forward those CMCs, EBCs that we got to TRL 5 into the combustor section, and the advanced turbine aerodynamics. And so with that, we're very excited. I think that, like I showed earlier in the presentation, if we're able to get really close to achieving those 2008 M+3 goals with this and the engine by 2029, it really is a good story that we were able to push the technology, and NASA was able to contribute both with our subject matter experts and facilities, not just funding, to push this where it needs to go and make a big step in technology when it comes to fuel-efficient single-aisle engines. Thank you.
Well, thank you, Tony. And please hold your questions. I'm sure you have some questions, but hold them. We have a Q&A panel session at the end where all the presenters and myself will be sitting on these wonderful chairs here, and we'll be happy to take your questions. The good news is we found Gaudy. She was unfortunately a bit double booked, so she was ending up sort of having two sessions in parallel. She managed to come here, so we'll go back now to the first presentation, please. The one which was originally planned. Yeah, that looks good. So let me introduce to you Gaudy Bezos-O'Connor. She's the project manager for the EPFD program at NASA. Gaudy is an undisclosed time at NASA, so I can't really actually mention that properly. So she must have joined at school because she's at 40 years of NASA now counting. So let her give her a round of applause. Apologies for the swap of the first and the second presenter, and let's see what Gaudy has to say.
All right. Good morning, everyone. Buongiorno. So today I'm going to be talking about the barriers that exist in order to enable megawatt-class electrified powertrain aircraft propulsion systems. And my project is focused on demonstrating on real airplanes an integrated megawatt-class powertrain system with two partners. So I'll tell the get off the stage chart, which is we are partnered with GE Aerospace, who has partnered with Boeing Aurora Flight Sciences to demonstrate on the Saab 340, which is the lower graphic livery, the blue and white Saab 340. And we have also partnered with magniX, who has selected Aerotech as their aircraft integrator, and they will be flying on a de Havilland Dash 7. Both partners, this is a cost-share partnership, plan to flight test their architectures in the mid-2020s. So shortly, maybe by Sydney, we will be able to share with you some actual flight test results. But what I wanted to focus on today is what are the barriers that actually exist to making electrified aircraft propulsion real? So next chart, please. Oh, wait a minute, I can do it. Okay, so I've broken these up into two parts. First, what are the technology challenges? And second, what are the integration challenges? And we've made a lot of progress on the technology challenges. As Tony alluded at NASA, we've partnered with the industry for many years to get us to a TRL 456 for some of the components that are needed to enable megawatt-class powertrain systems. And we've done lab-based work. We've done testing at NEAT. NASA Glenn Research Center in Sandusky, Ohio, has a high-altitude test chamber that you can bring your powertrain system and you can test it at altitude. And that is really the critical defining test at the ground level that will definitively say, are you a whole system that will minimize EMI and partial discharge of the powertrain system itself? That doesn't answer the question as to whether this will also buy down any risk with respect to EMI and partial discharge with the legacy aircraft systems. And that's another piece that has to be addressed also. So I'm going to walk through each of these, and you'll note that I've color-coded them depending on whether they're essential for weight reduction or essential for lifetime. And this lifetime piece is really critical because at the end of the day, after we as a team do these flight test demonstrations, there's still a lot of work left to be done. Reliability, maintainability, how do you actually get the infrastructure in place to ensure that we can monitor these systems as they actually fly in a commercial product? So let's go first with high voltage operations and altitude. This is where the NEAT test facility that we have in Sandusky, Ohio, has given us greater confidence. And both of our partners have either completed the test or are in test. So GE completed in 2022, and magniX right now is actually testing in the facility right now. And so I want to actually walk through the risk statement that it says. Given that arcing, partial discharge, and corona high power voltage transmission cables can occur at cruise altitudes or due to life effects, there is a possibility that the demonstrator could have power system failures resulting in potential loss of aircraft. This is a really big hazard, and so we're doing our due diligence to be credible to addressing high voltage operations at altitude with their systems at our test facility. The next one, and this is critical to being able to buy down the weight of these systems, because you can fill up a computer-sized room, an IBM, the original IBM, that size hardware, but then you would have no volume for people or cargo on a real airplane. The next piece is thermal management, and this is really the longest pole from a technology perspective, because the waste heat that's created by these powertrain systems, especially once you achieve at least 1 megawatt, but for a narrow body single aisle aircraft, you could generate up to 20 megawatts of waste heat. And that is a huge challenge that needs to be addressed. And the risk statement for this area is, given that the amount of electrical power required for the demonstration is unprecedented in flight and generates significant low quality, low grade heat, there is a possibility that there will be unforeseen challenges in designing a low parasitic power thermal management system. So this is something that is not a solution that one size fits all. It depends on the aircraft that you're actually going to try to fly, your electrified aircraft propulsion concept. So for Part 23 airplanes, it is more manageable. It could be through passive cooling. But for a narrow-body single-aisle aircraft, you're going to have to do active cooling. And so these are the trade space that has to be addressed as a community. The next one that I want to talk about that is a technology risk is battery system performance shortfall. For those of you that are actually working in the battery domain, aviation batteries do not exist at the power density levels that we need to be able to fly airplanes, at least the single aisle for sure. We can do it for general aviation aircraft, but this is a really big technical challenge. And I think the current chemistries, lithium ion, will only get us so far. And we may need to go to another type of chemistry that is years away from being real. So the battery performance shortfall is driving us to what I would call the most likely case, which is a hybrid electric solution. So it is leveraging both the gas turbine engine as well as the megawatt powertrain systems together, whether it is a standalone electric engine plus a gas turbine engine working in parallel, or whether it is an integrated powertrain gas turbine engine system flying to leverage the electrification piece of the solution for those key aspects of the mission. E-taxi, top of climb, don't really need it in cruise, at least for the single aisle narrow body, because gas turbine engines do the job really, really well. So the risk statement is, given that the battery pack requirements exceed current technology, there is a possibility that the battery system design does not meet performance requirements, resulting in higher battery weight and decreased vision vehicle performance. In NASA speak, that means a commercial product, the performance that it will need. So the key thing here is higher battery weight. That's another big problem with batteries. They're very big, and airplanes have just so much volume. You can't grow the volume of an airplane. And the trade then becomes people and cargo versus battery. And everyone's going to say, well, we have to ensure that we have revenue. So people and cargo are really the drivers to this. So we have to work the battery solution as an integrated system that addresses both the end user requirements as well as the vehicle performance to ensure safety and airworthiness. Okay, so now I'm going to switch over to the integration challenges that are in front of us to make electric aircraft propulsion real. So again, it's the same sort of construct. The blue lines are essential for life, and the green line row is essential for weight, and we must decrease the weight. So the first one that we call out is called the propulsion system integration. And this is the architecture you choose to integrate your electrification system with the current gas turbine system, whether it's a turboprop, a turbofan, turbojet. How are you going to actually marry both systems together? And the statement states, given that this electrical aircraft propulsion system is novel, and there is a possibility there are unforeseen conflicts in the turbomachinery integration with electric machines, which could result in reduced operability and large system weight that decreases the overall performance of the commercial product that you're looking for. So this is one that is going to be very specific to the actual market and aircraft class that you're targeting. So the solution is not one size fits all. I think you're going to see this as a theme in my talk, is that our project is trying to start the conversation as to what's the minimum, what's the knowledge that we've gained, but it needs further research and further experimentation and flight tests and analysis to get us to your solution set. The next one is powertrain system integration. So this is the actual powertrain, however you've chosen to design it, and there's a possibility that this powertrain system integration may not meet the electromagnetic interference compatibility or performance requirements, which will require a redesign. And then every time you say redesign, it costs a lot of money and time. And your supporters, financial supporters, as well as the community may go, no, we don't want to go there. But I think that we have a lot of knowledge, and we've gained a lot of knowledge in the last 10 years on the aspects that we must actually test and investigate and analyze to enable successful powertrain system integration. The last piece, and this is the piece that is really the key focus and the deliverable for the EPFD project, is aircraft system integration. I was charged by the Aeronautics Research Mission Directorate of NASA, Bob Pierce, to demonstrate the practical feasibility of integrating megawatt-class powertrain systems on a commercial aircraft. So both of my partners realized very quickly that such a demonstration couldn't really happen on an existing single-aisle narrow-body aircraft. The technology wasn't there. But the regional market was really ripe. It's the low-hanging fruit to enable a demonstration. So GE picked the Saab 340. It's a 2 turboprop aircraft. And Magnex picked a 4 turboprop aircraft, the de Havilland -7. And both of these do serve the regional market and are excellent platforms to test their architectures. So let's take a step back and say, well, where are we in electrification? Because it's been in the news, it's been lots of press and lots of accomplishments with respect to electrifying aircraft. And if you look at the recent past, we see that the majority of the work, almost all the work, has been done in the general aviation marketplace, Part 23, where you've been able to demonstrate up to 300 kilowatts of power as a retrofit. No clean sheet of paper has happened with respect to electrification. Then, just recently, in the last, in 2022 actually, a company did actually create a clean sheet of paper aircraft design, Eviation Alice. And what was if you have an opportunity to actually research this company, not that I'm advocating or endorsing this company, but what they did is, when they did their clean sheet of paper, they actually addressed how to structurally incorporate the actual battery system that they would need to fly their aircraft. So that's something to consider for those of you that are looking at new opportunities and how do you actually go from an existing retrofit opportunity to what could be a new platform, a new production line. And so they actually have integrated into the structure of their aircraft where to place the batteries. And it flew, and it also is a general aviation Part 23 aircraft. It flies up to 9 passengers. So it's a flight demonstration, so they're still in the midst of doing their due diligence to enable an airworthy commercial product. And now we have EPFD. We started this project in September 30th of 2021. We brought on board GE and Magniacs, and we're looking at megawatt class. So this is on the order of 1.4 nominally if you enable a two-sided demonstration. And it is on a retrofit, and it is a large turboprop single-aisle aircraft class, Part 25. So the knowledge that we're going to be gaining from these test demonstrations is not just ground tests and flight tests, but it's really credible engineering data that will help inform the community on how to actually create the standards that are needed to enable electric aircraft propulsion, airworthiness, and certification. Now, NASA's not responsible for regulations and standards, but our partners are engaged in the communities that are actually going to define what are those standards that enable megawatt class powertrain systems. And so this is the path to certification, and our project has, we are trying to identify, we have asked our partners to tell us what are the priority gaps that they're working towards their commercial product that EPFD can help provide the data so that it can inform the path that they want to take. So this is really, really, really critical for us, and it's to enable the introduction of megawatt class electrified aircraft propulsion systems into the transport category aircraft. So what is EPFD? And I've already talked about this, so I'm just going to be really, really, really high level. It is to demonstrate an integrated electrified powertrain system in flight using industry platforms. This is their technology, their architectures, their ideas. We are partners in the actual integration and ground tests. We are responsible for airworthiness. NASA will issue the airworthiness flight certificate. Again, we're leveraging. The scope of this work is to take this knowledge that we gain with our partners and do a forecast, similar to what Tony has done in the power extraction and in his phase 2 demonstration. We're going to take all of these technologies and we're going to do a rack and stack vision system assessment to say what's the potential impact. And with Tony's project and my project together, we're going to be able to have a forecast of what's possible to have electrified powertrain systems with power extraction for the single-aisle narrow body case. The benefit is to accelerate U.S. industry readiness to transition electric aircraft propulsion-based concepts to commercial transports. It's to reinvigorate the regional market. If we are successful in actually being able to shape the regulations and standards, our partners are, not NASA, we will be able to redefine what is a regional commercial market. Could it be that the hub and spoke gets more efficient? Could it be that us as passengers get to go to where we need to go with less costs? Because electric machines aren't as costly to operate as turbomachinery-based systems. And I guess the last thing I want to do is we want to strengthen the single-aisle market. You know, this is an option. It's not going to be a one-size-fits-all, but it will give the community, the aviation community, the choice of making hybrid electric. It may work really, really well in Europe. It may work really, really well in island-type countries that have short hops. It may be harder to justify for a LA to New York flight because significant portion of the flight profile is in cruise, and turbofan and jet fuel are very efficient systems. So I just wanted to just share a snippet of what our industry partners are working on. It is their story to tell, and so I'm really not going to be able to provide any details other than a really high overview. But I just wanted to share with you GE Aerospace's approach to this, and I think Tony's presentation did allude to that a little bit, is that our flight demonstrations are going to happen in the mid-2020s. It will be on a Saab 340 test bed. And it is an integrated hybrid system with the CT7 engine. So it's an engine that GE already produces. So this is another piece that for the propulsion OEMs that are out there, you need to look at your architectures and see what is the right decision path for you. Is it an integrated system within your current turbo machinery, or do you need to have a separate retrofit type of configuration? The GE Aerospace and Boeing Aurora Flight Sciences partnership is really strong. Both parties bring excellent expertise to the table. Boeing Aurora Flight Sciences, for those of you that may not know the company, their expertise is doing technology demonstrations, leading edge novel technology testing. And so it's a great marriage, and working with the NASA team that encompasses 4 NASA centers, Langley Research Center, Glenn Research Center in Cleveland, Ohio. Langley's in Hampton, Virginia. Glenn is in Cleveland, Ohio. Armstrong Flight Research Center is at Edwards Air Force Base in California, and Ames Research Center is in San Jose, California. And so their focus is to demonstrate feasibility and reliability of hybrid electric propulsion systems. Their future product, right? So all of these demonstrators are tied to a commercial product that is the desired outcome for each of our partners. And so they're looking at the RISE program. It's their CFM RISE program, which Tony explained a little bit earlier this morning, that is going to take that hybrid electric knowledge, and they're going to integrate it into their RISE architecture. And so this is to enable SAF, as well as possibly hydrogen energy sources. And this is one of the things I didn't really talk about a lot, because it's not the focus for EPFD, is batteries are not the only solution. And I think that for the regional marketplace, it's definitely an and. So you need electrification and possibly hydrogen and possibly SAF. And it could be SAF and hydrogen and electrification. It's an and for the solution set. And this partnership will hopefully give GE the opportunity to craft the designs and the hybrid electric capability that they're looking for their missions. So magniX, which is our other partner, so this is a very small company that started in Everett, but it's actually been in this business since 2007. David Sercombe gave an excellent overview of the work that magniX has been doing yesterday morning. And their approach is different, right? So they started with, we built our system, our Magni system, and we've tested it on a variety of platforms. So they started with the E-Beaver, they went to the Caravan, they've done a Robinson 44, they've done a Dash 8 with Universal Hydrogen, they've done the Eviation Alice, and through all of these demonstrations, they've gained a lot of operational knowledge and integration knowledge. But they recognize that for them to actually be able to create a commercial product, they needed to actually do a demonstration that was based on credible engineering knowledge and test methodology development. And EPFD's opportunity came across their desk, and they said, this is the right time to leverage all of our Part 23 knowledge and actually get into the Part 25 field. So the Dash 7, the de Havilland Dash 7, it's a parallel hybrid concept that they're going to go to do. I think I can actually press, can I press this? Perfect. So the Dash 7 actually has 4 turboprop engines. And so what the plan is for them to do a 2-phase flight test program. The first is to do the one side. So it will actually mimic the FAA regulations, 1 engine out, gas turbine engine out, condition. So they'll have 1 electric machine and 3 gas turbine engines. For the second phase of the program, they're actually going to have 2, 1 on each outboard, and they will be standalone electric machines, electric engines, and they will work in tandem with the gas turbine engines to deliver the power. Now, one of the things that's really, really key for them as a provider to the marketplace is that they're estimating right now, based on all of their flight test demonstration experience, a savings of over 45% off of the baseline aircraft. They've partnered with Air Tindi. It's actually one of the largest. It's the largest Dash 7 fleet operator in Canada, and they actually have leased this airplane from Air Tindi, and this will be knowledge transfer right to an actual commercial airline or aircraft operator. I'm not sure they really are an airline. They do a lot of cargo delivery, but I think they also have passengers. The Dash 7 can carry up to 50 passengers. And so they're looking to demonstrate 200 nautical mile mission. So their configuration that they're set up for is not only to just demonstrate it, but they're actually doing it to a realistic distance that is commercially viable. And they're also developing the battery system. The Samsung 300 is what the system is being called, and it will be an aviation-grade battery. So I think I will close with, this is really exciting times for EPFD. We have two fantastic partners. I look forward to be able to share more progress, where we have a very robust integrated ground test program, and hopefully in 2026 in Sydney, I'll be able to share more data. So thank you very much.
Okay, again, same procedure. Keep the questions for later. We'll be all sitting here. Definitely interesting talk. Thank you, Gaudy, for this. So the third presentation, please, technique. Okay, so we have Takashi Yamane now with us, who's the project manager for the Encore project in JAXA Aerospace in Japan, which actually also is focusing on advanced core technologies, mainly hot end combustor and turbine materials and design technology. So, floor is yours.
Good morning, everybody. It's almost noon. And I start with my personal concern on the air transport because I'm very anxious about the baggage problem, because I put my nectar in my baggage, but my baggage have not arrived yet. So it's my concern now, but let me come back to the environmental issue. Core engine continues to be a power source for future engine with advanced configuration, such as much higher bypass ratio turbine engines, unducted fan engines, and electric propulsion system with powerful generator. Technologies for smaller size, higher overall pressure ratio, and higher firing temperature are keys for future core engines. The smaller core is affected by the viscous thrust. Higher overall pressure ratio is necessary for better thermal efficiency of Brayton cycle, of course. The higher temperature is for the larger power. The higher temperature may increase the production of the thermal NOx and may increase the cooling air for turbine, which will lower the efficiency. JAXA is working with Japan's aero engine industry partners for core engine technologies. The Encore project is the R&D project to enhance the competitiveness through technologies that reduce emissions of NOx and CO2. Encore stands for Environmental Compatible Core Engine Technology Research Project. And we started this project in 2018, and now we are near the end of our project. We have two targets of the project. One of them is ultra-low NOx lean burn combustor. The low NOx combustor developed by JAXA and the industry partner is enhanced to the technology for a practical engine, and the world's lowest NOx emissions performance is demonstrated. The other one is highly efficient high-pressure turbine. By increasing the aerodynamic design technology of turbine blades, high temperature heat resistance material technologies, and cooling technology developed by JAXA and the industry partner. The turbine efficiency that can compete with the major engine manufacturers is demonstrated. These are the goals of Anchor project. The target is the next generation engines for 737 or A320 class aircrafts. That is similar to the HYTEC just we have presented. The target of the combustor is the world's lowest NOx emissions. 80% lower emissions than ICAO Type 8 standard at the target engine LTO cycle is demonstrated by the annual combustor test. And the industry partner of the combustor part is Kawasaki Heavy Industries, KHI. And for turbine efficiency comparable to the highest performance of the current engines is the target. The turbine efficiency values are not, absolute values are not publicly disclosed by engine manufacturers. And our target values cannot be publicly disclosed either. But our aim is to get the competitive efficiency, which would be the highest value. The adoption of CMC, ceramic matrix composites, is one of the measures to improve the efficiency. So the demonstration of CMC turbine vane structural integrity with a surface temperature of 1300 degrees C or higher. The partner for the turbine part is IHI. These are the technologies for our ultra-low NOx lean burn combustor. The left figure roughly shows the NOx emission status. Most of the current engines clear the ICAO Type 8 standard, but combustors with less NOx are necessary for the future, higher overall pressure ratio and higher temperature engines. So we have set our goal to ensure it will not become obsolete for decades. This is the cross-section of our combustor. The number one is the stable lean premixed combustion essential to lower the NOx emissions. The primary nozzle consists of a pilot fuel line and a main fuel line. They are arranged concentrically. The pilot flame is a diffusion flame, while the main is a lean premixed combustion. The lean burn can avoid the stoichiometric condition, which is the highest burning temperature, and the cause of the thermal NOx production. But it sometimes causes the harmful combustion oscillations or the flame out. The pilot flame is necessary for a stable lean burn, but it should be minimum because the diffusion flame produces more NOx. And at high power and temperature conditions like max takeoff and max climb, the main flame temperature goes higher. At these conditions, the fuel from the secondary nozzle is increased to suppress the local temperature rise. Number two is the application of the CMC panels to reduce cooling wear. The reduced cooling wear can be used at the primary nozzle for less fuel ratio combustion. Number three is the prevention of the carbonization of fuel in the fuel passages. When the main fuel is stopped, the remaining fuel in the passages may be carbonized by the heat. keeping the fuel passage temperature low is important and is done by the design of the layout of both main and pilot passages, because the pilot fuel is always running and it will cool the overall fuel passages. And number 4 is the fuel control of multiple nozzles. We also have tested some transient combustion stabilities. For example, starting with the pilot-only combustion, then increasing the fuel of the main with smooth temperature rise. Until 2020, we have completed the development of the primary nozzle. The verification of the CMC panel integrity using the single sector combustor is also completed. The NOx emissions were below our goal, with some margins by both single and multi-sector tests. And we are now at the final stage of the verification by the annual combustor. Because of the very high production cost at this moment of CMC, the CMC panels are not used for the annual combustor test, but the emission evaluation will be adjusted so that the conditions are equivalent when the larger airfoil is supplied for the combustor liner cooling without the CMC panel. Here are some pictures of our current experiments of the to demonstrate low NOx performance in an annual combustor. We are currently conducting experiments of this combustor. It's the CAD model, and from this CAD model we have made this combustor. And as you see, by comparing with the height of this person, he is the key person of the combustor development, and the combustor is the full scale size as big as the target engine. From now is the turbine part. This picture roughly shows the operating vane surface temperature of turbine. The operating temperature of turbine materials have got higher as the development of superalloys progresses, but its rise is gradually reaching a plateau. For our turbine vanes, we use the CMC, which has a potential up to 1400 degrees C as the material itself, with the aim of achieving operating temperature exceeding 1300 degrees C. This temperature can reduce the cooling air. Then it contributes to lower the mixing loss between the hot gas and the cooling air. We also tried to make a 3D shape vane, but this illustration is exaggerated. And drilled film holes, which are similar to those for the state-of-the-art metal vanes. We verified the integrity of the prototype CMC vanes through high temperature and high pressure gas flow test. The other target is the rotating metal blades. The aerodynamic loss is reduced by the advanced blade shape design. The mixing loss is also reduced by the advanced film holes, with further enhanced effectiveness and by the improved internal cooling structure. And finally, the aerodynamic designs of vane and blades are tested by the rotating turbine rig, and adiabatic efficiency is verified. Until 2020, we have made the aerodynamic shape designs for vanes and blades. And various strength tests of CMC, including destructive tests such as static load and fatigue tests and high temperature. This picture is an example of test specimen with film holes after the test. We also have done the selection of film holes by measuring the film effectiveness and the pressure loss near surface precisely by the experiments. After the design, we confirmed the estimated efficiency gain will exceed our goal. Our goal is this blue one, and even for the worst case, then we manufactured vanes and blades for the final verification. And we completed, until the last March, we completed the project activities for the highly efficient high-pressure turbine. These are the summary of the achievements of the turbine part. The prototype CMC vanes are here, were successfully manufactured. They have a small bow shape, and a smaller loss trailing edge shape, and we also succeeded to diffuse film holes which are equivalent to the latest hole for the metal vanes. And more complicated hole shapes were also possible. The rotating blades have a tip shape which reduces the secondary flow loss between the stationary shroud wall and the blade tip, and also a low loss trailing edge shape. And advanced film holes show a better film effectiveness and a smaller mixing loss compared to the latest diffuser film holes. The CMC vane was tested in the hot gas to check heat resistance and the cooling design validity in the combustor test facility. The hot gas around 1600 degrees C comes from the upstream combustor, and the cooling air is supplied to the internal cavity of the vane and goes throughout from the film holes, so that the highest surface temperature is not lower than 1300 degrees C. The flow passage was made to be equivalent to the cascade flow. And after 10 hours, the tested vane showed no damage. This picture is after the test. It looks dirty, but it is not the damage of the CMCs. It comes from the test facilities. The thermal cycle test at atmospheric pressure condition has also been done to check the highest stress effect against the strength of the vane. This test is to simulate the flight cycles. The test result was also successful after 1,000 cycles. The turbine efficiency was tested by the rotating turbine test facility. For this test, the temperature is not as high as the actual turbine, so CMC is not necessary. The similarity condition of the Reynolds number, Mach number are ensured, and the temperature ratio between the hot gas and the cooling air is also met. This is very important to take the effect of the mixing loss by the secondary flow air correctly. Our rotating turbine facility is made to be able to do that, and we took the precise rotor exit condition. This is the total pressure distribution, and we can see the loss red regions here. Unfortunately, I can't tell how much we got the gain value because it's a sensitive figure which relates to the partner company's competitiveness. But we got a much higher efficiency. The target was this, and we got a much higher efficiency than the goal we set at the start of the project. And in the final two slides, I will show the contribution of our technology. The first one is for low NOx. This chart is shows the NOx emission of the real engines plotted against the tested date. This graph is plotted using the ICAO emission data bank. So it's the, it's the real values. And all marks are for the real engine data. The latest engines, NOx values are smaller than the Type 8. And you can see the latest engines of the, for example, these lean burn combustors and Pratt and Whitney's latest alkyl combustors are competing. It seems that the discussion on the next type standard has not progressed yet, but in 2019, ICAO independent expert integrated review has set the midterm goal around here. And our goal is much lower than the midterm goal, and our lean burn combustor technology will be ready for our engine test after we complete the annual combustor test. We hope an engine with our technology will be entered into service during 2030s. And this is the final slide, the turbine part. We made an estimation of fuel burn reduction by the improvement of turbine efficiency as well as the reduction of the turbine cooling airflow. Cooling air reduction will also contribute to the improvement of the total engine performance because the compressor work is used to make the pressurized cooling air. By assuming a 500 nautical mile flight of A320 class aircraft, the fuel burn will be reduced by 2.3%. One of the scenarios of the waypoint to 2050 scenario 1, 22% reduction is required by the technology development, and our contribution will be equivalent to 1/10 of it. Thank you very much for your attention.
Thank you, Takashi. If you want to take a seat to the far right, and if the other two presenters want to come up, take you in the middle, Tony. So as I said, I hope you saved your questions and comments, and we are open. It works. It works. Very good. So we're very open to questions from the audience. It's very hard to see you. That gets better. And there's already a raising arm, and I think there's somebody with a roving mic coming. Here we go. Please state your name and affiliation. Maybe stand up that people could see you and then get an idea.
Thank you. My name is Yoji Okita from JAXA, the same colleague. I have one question about HYTEC project, the Tony. You mentioned you're trying to apply CMC EBC system to high-pressure turbine as well. And you mentioned, but which part do you actually try, vane, blade, or shroud? And it's cooled CMC or uncooled CMC? Thank you very much.
So I can't get into too many specifics, but I know we're looking at CMC vanes as one of the components. There are some CMCs flying now, so I think we're looking at bringing vanes into the mix. The ultimate goal, I guess I could say it this way, the ultimate goal is to have uncooled, obviously, but it's hard to say if we're going to get there. Really, that would be the most efficient solution, but I think there's still some distance to go on seeing if the materials can survive that long with no cooling at all. So I think the near-term goal is probably to reduce cooling, but the long-term goal is to eliminate it altogether.
Thank you, Tony. Any other questions from the audience? To shield myself. Rick, over here in the front. So you're going in the wrong direction? There. Okay, so you have this one first. You go first, and then we have Rick thereafter. Is that okay, Rick? You're good. Okay.
Hi, Arthur Orton from the US FAA. My question's for Tony. In the sort of system level assessment you showed of the projection of the benefits of HYTEC, One of those was on the increased bypass ratio, kind of given the baseline Pratt and GE designs. Was that increase in bypass ratio all coming from the shrinking of the core while holding the fan diameter or engine diameter constant?
Yes, it was. I should have mentioned that, particularly because there's not a lot of real estate on either airplane to make the fan much bigger. I think they've made them as large, maybe a little bit, particularly not on the MAX, but no, so the increase from 8.6 to 10.8 was assuming a same-size fan, and that the bypass ratio was all gained from the core getting smaller.
Maybe I had a comment here. So there is still a bit of real estate on the airplane, so you can actually go a bit up in fan size, but not much. Not much. So specific thrust is still a play. Rick, now, can we go here in the front? The young gentleman with the beard.
Hi, Rick Parker, Singapore Aerospace Program. Question to both Tony and Takashi, also on the CMC materials. So what particular material systems are you looking at? Is it 6-6, SiC alumina, alumina? So that's a question to both of you. Question specifically to Takashi on your very interesting combustor concept. It looks very interesting, looks a novel design, but it looks very heavy. Have you got a datum of that against a similar annular combustor today to see how much extra weight you put on with all the additional burners?
What CMC? The CMC technology is based on our Japan industry partners. So the CMC itself is not within our project scope, but Japan industry has developed, improved the infiltration process to take the higher temperature resistance. And for the combustor configuration, putting the secondary nozzle may make a complicated structure and may increase the weight, as you said. So we also are thinking about that. And before our combustor with the secondary nozzles, in the realistic solution will be the combustor with only the primary nozzle comes first, I think. Am I answered your question?
I assume you had 6-6 CMCs? You can't comment. Okay, okay. Good. Maybe a question on top of what Rick just asked. So you understand that you have secondary nozzles in your combustion design. I didn't understand why you actually put them perpendicular into this. Was this just size constraint, geometric constraint? Because it looks you have a very complex way of then getting airflow to a lean burn nozzle, which needs a lot of air to manage. So you have it axially and you have it radially. So that was a surprise to me.
Yes, I know there are various, location of the secondary nozzle is have been developed in the past, but our researchers put simply on the top of the combustor liner because putting the nozzles there was very simple, and the angle didn't have made any difficulties for the combustion. So we are continuing to use that position. No answer with me.
Good. Any more questions? Up there, at the top, to the right. Okay, you have a very fast one coming here. And then you're second over there, I see you. Okay. But you're second, he's first.
That was fast. Thank you very much. Hi, my name is Asteris Apostolidis from Amsterdam University of Applied Sciences and KLM Royal Dutch Airlines. That's a question to Wal, the panel. Even at this level of TRL scale, like during the development, Do you take into account any aspects around maintainability and operability, or those kind of requirements come later? Like, and I'm speaking from the perspective of the operator, since like we've seen examples of different products that like they perform poorly in the past when it comes to when they come into operation. And that's it. Thanks.
Very good question. I'll maybe actually give a general statement because I hand over, I think, to the two of you. I'm pretty sure that operability sort of requirements are an integral part of actually scaling the compressors, the combustors, and the turbines in those core and developments, and also on the electrification. I'm pretty sure there will be, and you've seen that in Gaudy's presentation, a good line of thought going into the risks, risk mitigations, and the FMEA. So it's an FMEA of the failure mode effect analysis of having electrical systems not working or failing. So I'll give a handover to you.
Yeah, operability is the key piece of it all, and part of, especially with the hybrid electric part on the core, number one, you have to make sure all the core sections, interact with each other. When we're doing compressors, turbines, it all works together as a system. It gets more complicated bringing in the electric machines too. So operability is the most important thing, being able to operate the core and the engine, adding on this additional complexity with electric machines. So that is the primary goal of this integrated core, is to show that all these things work together in a manner that it can go into production once we're done.
Yeah, the only thing I would add is, so our demonstrations are TRL6 for the actual powertrain system on the aircraft, but operability is tied directly to hazard mitigations, human factors integration, how the crew and the pilot and the actual systems will get charged, will actually operate, and it's a really key piece of demonstrating feasibility that these powertrain systems can be built and integrated on aircraft. So we're going to have a lot of lessons learned, and in one of our design reviews, one of our independent review board members said, well, we can use this to start creating the training manuals and the operational manuals that are going to be needed for these systems to operate in the real world. So this is really important.
I don't have any, because my project is focused on the specific part of this technology.
Dwelling on that point a bit, maybe for the audience as well, it's quite important, especially on the hybridization and electrification, that you look at it and say, okay, I'm adding something to the system. It's fundamentally an off-design optimization of the overall product, unless you go to things like parallel hybrid, where you actually have an additional full power source linked to it. And on the simple hybridization, I would think it's all about making sure that what you're adding doesn't become absolutely safety essential. Because if it comes, you actually have to show reliability, which is far higher than you actually can do today without all these flying hours from all the other stuff. So it will be things where you do ground idle, flight idle management, where you can actually live with it not working. Could be one element. On the parallel hybrid, which Gaudy showed, where you clearly actually have, I think, effectively a turboprop gas turbine on the same gearbox as the electrical powertrain. I think that's quite nice because, the gas turbine can do its stuff and the electrical powertrain will actually go into the same gearbox, and you don't have complex control logics there. So to a certain extent, if you then actually have a failure of the electrical powertrain, you have to have an overall aircraft case which can live with this in an element. That's maybe a way to look at it. Any more questions?
Yep.
Sorry, I promised you're coming. Here
exactly. Lorenzo Mazzei, Ergon Research. I don't know why I'm making this question, because I know the answer is no, but is anyone from the three speakers planning to share some data similarly to what NASA did for the Tripoli engine in the 80s or the 90s? I don't remember. Because that would create a lot of opportunities to do validation, benchmark, publication, and so on. So I'm not speaking only of 3D geometries for CFD simulation and experimental data. I'm speaking also about the result of the hybrid electric system. That would be extremely nice to calibrate or validate 1D models, for example. Thanks.
So it's not no, but it's not yes. It's somewhere in the middle. One thing we did on HYTEC was we required all of our contracts to have not only a final report that has all the proprietary stuff that only we can see, but that they have to provide a report that will be publicly available. Obviously, with a lot of the technology redacted, particularly when you go to TRL 6, right? A lot of it's going to be company proprietary. However, we're doing the same thing with our phase 2 contract and the core demo. There are pieces that we will make public. We will make our results public, obviously, of how we did. I can't really say, because it's going to be a negotiation as we go forward, how much actually is going to, how much data will actually be public. But we have the phase 1 contracts that we have finished. We already have those public reports available for the ones that have completed. The 3 of them have completed. So there is a certain amount that we are going to make public, but it's not going to be everything on all the data. So it's somewhere in the middle. Not a great answer, but it's better than no on all of it.
So my answer is kind of similar. The industry proprietary data is theirs, and we will protect it at all cost. But we do have technical performance measures that are in the public domain that were the metrics by which we selected the companies to be our partners. So those TPMs are going to be reported. We're going to have what we call a public domain, forecast vehicle, 2035. And if these systems, fly as we expect them to fly, we'll be able to forecast what a projected state-of-the-art vehicle in 2035 would look like. So you'll get some data. It truly is up to the companies to decide what they would like to disclose. I think another piece of this is that we have such a close tie to the ASTM and SAE communities. Our partners actually sit on those boards. And I think that from my perspective, it's more important that that community talks of what they learn and their experiences to help inform what are the regulations and standards that we are going to need to enable successful electric aircraft propulsion adoption. So that's really the holy grail of all of this, is this data will help the community understand what they need to do, what are the test methodologies, and how to actually craft the means of compliance to making electric aircraft propulsion concepts commercialized.
Yes, for our combustors, anyway, we are now preparing for the publish some papers, but for our combustors, I think our emission measurement data would be published, but the operating condition comes from their industry partners, so it will be disclosed. And perhaps one type of our combustor shape could be published. And for the turbine part, its efficiency value is completely disclosed, and the precise shape will be also a delicate one. So we are discussing what part of our achievement can be published or not at this moment. Yes.
Thank you. Any more questions from the audience? Rick, again, of course, yeah. I'm sure they'll find you again. We'll get them some sports in here. You doing a race? No, it's only one coming.
Thank you. Sorry, I just wanted to ask a quick question for Gaudy. Rick Parker again. You mentioned one of your risks, which we're well aware of, is the risk of arcing, corona discharge in these high voltage systems at altitude. I just want to understand, you mentioned doing the altitude testing, which is excellent. Have your partners already set their voltage, and this is a sort of go, no-go test that says, well, will it work or won't it? Or is the idea of the testing to say, look, you can work to this maximum voltage before we see a problem?
So both partners have established their architectures, and they have done component level EMI, partial discharge testing, before they went to the integrated ground test system. So they've established it, and so they know what they would like to get as a performance. So they've set the design spec. They've come to the NEAT facility in Sandusky, Ohio, test it. The facility itself has the capability to test the full powertrain system to 45,000 feet. So depending on what your architecture is, you can test it and do the measurements that you deem are important to validate that it will operate safely. High voltage, our RFP had a target of 800 volts. So we're really talking significant architecture that has never been tested before in an aircraft environment.
Yeah, we did some testing at Manchester University a few years back on some of our electrical systems, and we started to hit problems around 700 volts, I remember. So yeah, 800 is an interesting area to work in. As a result of that, we actually developed some novel insulation for all the cables and things, which got us up to a higher voltage.
Yeah, I mean, it's really an important piece to making this powertrain successful. There is going to be Electric Aircraft Technology Symposium, EATS, in partnership with IEEE in June of next year. And there's a technical committees focused on how to make high voltage systems safe and prevent partial discharge and EMI interference.
Very good. Thank you, Gaudy. Any more questions? We have a JAXA question here again. Yeah, okay.
Thank you. I'm Yojo Kita JAXA. Another question to Dr. Bezos-O'Connor for electrified propulsion. You mentioned the thermal management is one critical technology to realize, and you mentioned also the passive cooling is not enough anymore, and you mentioned active cooling may be needed. So can you comment more, if you can you comment more details about what kind of active cooling you're saying?
Well, the design solution varies depending on your architecture and the aircraft you're actually going to put it in. It could be cryogenic, it could be other types of active pool cooling. I can't disclose what our companies, our partners are doing, but in the literature, it does provide the trade space of what you would need to do to have active cooling for thermal management of high voltage, large megawatt powertrain systems.
Okay, thank you. Any more questions? I think we're starting to compete with the lunch. If that isn't the case, I can't see any raised hand anymore. So I would like, first of all, to thank the audience for bearing with us, for the small changes we had to do in the order of the presentations. I'd like to thank the presenters for their excellent talks, and would conclude the session hereby. Thank you very much.